Welcome back to all the fellow learners of chemistry. Last classes we have understood the importance of conjugated structures in organic molecules. Remember, whenever there is conjugation, we came to the conclusion the electrons are delocalized. And delocalization has stabilizing influence on the molecule. Therefore, by this time, you must have acquired the necessary grip over this term conjugation, how to recognize conjugated structures, and once you recognize the conjugated structures, keep on writing different resonating forms that are possible there. And you must also know from the rules of resonance how do you identify the most stable resonating structure and the next structure which is less stable, so on and so forth, such that my hybrid molecule is a combination of all of them. The most stable one contributes most to the hybrid structure. Therefore, focus was on definitely on stability only. Conjugation leads to delocalization, and delocalization appears to impart stability to the molecule. Now, this correlation between delocalization and stability, we shall try to revisit today with reference to benzene molecule. That means benzene is, as you are aware of, is an arch example of aromatic molecules. So we want to check out what is the scope of this correlation between an aromatic molecule and its stability. So what I wish to do is I will take some molecules which are structurally related to benzene and try to work out with the help of thermodynamic data. Remember, thermodynamics is a very crucial topic. It gives a very good theoretical understanding of many an aspect in the lab or in nature. So what I'm going to do today is I will take up a molecule cyclohexene and try to add hydrogen to that. What is cyclohexene, please? This is my cyclohexene. This is cyclohexene. Of course, it is not conjugated structure, but again, as I told you, I'm revisiting the concept of conjugation with reference to cyclic structures. And if I take this and if I add hydrogen, this is a typical reaction of an alkene. We can expect that hydrogen acts across the double bond and you will get a saturated carbon, hydrocarbon. So that molecule formed is a cyclohexane. Cyclohexane. And we can measure in an experiment what is the amount of heat that is liberated. That is called as enthalpy of hydrogenation. Enthalpy of hydrogenation with the symbol delta H. And this figure is minus 28.6 kilocalories per mole. This I can measure, and this also I can estimate. Estimation means I have to go back to Hess law of thermochemistry, which is part of law 1 of thermodynamics. Remember, in Hess law, we have assigned for each bond, a discrete bond, a specific energy. Therefore, I can understand what is the energy of this and try to estimate what is the amount of energy that is liberated. So I have this measure, theoretically estimated, and experimentally also I am getting the same thing. Nothing wrong. That is the behavior we normally associated with an isolated double bond. Next, I want to take two double bonds now in a cyclic compound again. The focus is certainly on the cyclic compound. So what I am now trying to do is I will take now a cyclohexadiene. This is cyclohexadiene. The double bonds are taken twice, but they are not in conjugation. Therefore, if I am to go for hydrogenation reaction again here, I need to take 2 moles of hydrogen here, such that this molecule is formed, cyclohexane is formed. And it is not a surprising element. The enthalpy of hydrogenation now should be double the value that we got earlier. And within the experimental error, we get the value which confirms what we are talking in terms of Hess law or in terms of which is getting confirmed experimentally. So the enthalpy of hydrogenation now, delta H will be twice of it. That is minus 57.8 That value is minus 57.4. 57.4 kilocalories per mole. This is nearly double the value that we got for cyclohexene. So cyclohexadiene, we get the value of minus 57.4. Nothing unusual, nothing surprising. Now what I wish to do is, I will, instead of taking these two double bonds isolated, I wish to convert that to a conjugated system now. Therefore, now instead of taking 1,4-cyclohexadiene, I wish to take 1,3-cyclohexadiene now. So what does it mean? I will rub off this and I will rewrite now entire thing. I will take now cyclohexadiene with 1,3 locations here. So my molecule should look like this. This is 1, 3 cyclohexadiene. Molecular formula same as that we have taken for 1,4-cyclohexadiene. Now to this again I will be adding hydrogen required as per the number of double bonds. I will get cyclohexane as expected. But if you again measure experimentally what is the amount of energy that is liberated here, experimentally, I am getting a value of minus 55.4. The delta H for this is minus 55.4 kilocalories per mole. It is slightly shorter, slightly smaller value compared to what I got for 1,4-cyclohexadiene. That means some stabilization we can observe in a conjugated system as expected even for non-cyclic systems. The behavior is similar to what we have discussed in the earlier classes. Conjugation appears to give or impart some stability for this. Now I wish to take a molecule with an extension of conjugation. Therefore, my next molecule is this. My next molecule is, again I am taking a cyclic 6-member cyclic system, a double bond, and a double bond here. This is 1, 3, 5 cyclohexatriene. Cyclohexatriene. Now again I will carry out hydrogenation for this reaction. I am not exactly telling the experimental conditions under which we carry this, because once I am calculating delta H, which is a state function, we need not bother about the root of the reaction. If I carry this reaction, again I will get cyclohexane, and the delta H value and enthalpy of hydrogenation value that I am getting is, delta H for this value is minus 49.8 kilocalories per mole. Minus 49.8 kilocalories per mole. This is much lower. In fact, if you compare this value for cyclohexadiene, remember what was cyclohexadiene value I got here earlier? This was the cyclohexadiene, and if you add hydrogen to this, what is the delta H value I am getting here? This is minus 55.4 kilocalories or so. That means what I have invested for 2 double bonds, and once I see 3 double bonds, there is no correlation. It is not somewhat slightly more stabilized. Here the stabilization is immense. Therefore, you must understand the cyclic conjugated system in the case of benzene is showing that extra stability which I cannot normally explain or justify in terms of simple resonance theory or a simple statement that delocalization gives you stability. That is, I can no longer make a statement that benzene is coming from 2 kPa structures. I cannot any longer resort to simple resonance theory here by telling these are my 2 kPa structures. This is one and this is one more, if you remember, double bond here, double bond here, double bond here. Therefore, both are contributing equally. Therefore, my hybrid is having equal contribution. There are no charges here. What all that you recollected about resonance, rules of resonance, you can again revise until this benzene is stable. But I don't think, in spite of that, that extraordinary dip in the value from the expected to what I get in the measured is about 36 kilocalories per mole. It is not 1.8 kilocalories as we encountered when we have compared 1,4-cyclohexadiene with the 1,3-cyclohexadiene. That means benzene or a cyclic conjugated system appears to impart high amount of stability. Therefore, what we now have to do as science students is we must take some more cyclic conjugated systems and again check out how do they behave in a particular reaction. Suppose if all those cyclic compounds which are conjugated have identical behavior or they behave differently, we have to verify that. So my next agenda is having understood benzene molecule which is behaving differently compared to what we have seen for conjugate systems here. I want probe by taking some more cyclic conjugate systems, hydrocarbons. Now, I wish to add one new point here. The cyclic conjugated hydrocarbons, cyclic conjugated hydrocarbons, and benzene is of course coming under that category. They are given a name. They are called as annulenes. Annulene. Annulenes. This is the name that we normally give for any cyclic conjugated hydrocarbon. In that case, just now we have concluded our discussion about benzene. Therefore, benzene can be called as, what is benzene please? It is nothing but 1,3,5 cyclohexatriene. Common name is more popular and more apt also. And this benzene molecule in terms of this is called as 6-annulene. 6-annulene. And we realized the annulenes are showing extra stability. So we want to consolidate that case or go into deeper aspects and try to check out the stability of a cyclic conjugated system or an annulene molecule. In this process, we shall take at least two important annulenes today to get a correlation between stability and conjugated structure. What I am now going to take is one more annulene which is having conjugation and cyclic, of course. That molecule I wish to call that as 4-annulene. 4-annulene. That means this is a cyclic conjugated system with 4 carbons, squarish. Therefore, that is cyclobutadiene. This is the structure for that. This is cyclic structure. One double bond, gap, one double bond. I think this is conjugated, right? Therefore, once it is conjugated, what's the next thing is? We expect they will have delocalization of electrons. That's what we have earlier understood that point. And delocalization must give stability. Now, if you consider this molecule, it is a sort of surprising thing here. It does not show any symptoms of stability, even though it is cyclic conjugated here. In fact, this particular molecule is difficult to prepare also. Suppose if you prepare this molecule, immediately it undergoes Diels-Alder dimerization. Dimerization means its behavior is not corresponding to that of benzene. You don't expect two benzene molecules to dimerize just like that. As a matter of fact, I can prepare this molecule in a very low concentration at a very low temperature and store those molecules or trap this molecule in frozen argon. That is, I must take so many parts into consideration, so many concerns I need to show such that I can isolate cyclobutadiene. But for that, it cannot survive. It will immediately undergo dimerization. What does it mean? This is cyclic conjugated system, but it does not show any of the expected behavior as we anticipated from our understanding of the benzene molecule. This does not show any stabilization. So what is the first statement we made? There may be some correlation between conjugation and stabilization as we have encountered for non-cyclic systems. Then we have shifted to cyclic systems. Benzene was showing that stability enhanced. Whereas in the case of cyclobutadiene, it does not show any of the features of stabilization even though it is conjugated structure. It is a sort of anticlimax for us. Let's take one more molecule and see how does next annulene molecule behave. That is again I have to take annulene only because my idea is to take up cyclic system, try to understand. Okay, now things have become slightly what's called hazy once you have taken um, butadiene molecule first. Now you take one more molecule that also must be annuline, and that molecule is 8 annuline. 8 annuline. That means this is a cyclic compound containing 8 carbons. So I am having here what is called as cyclo octa. 8 means tetra ene. This is the molecule, otherwise 8 annuline. So how does this structure look like? I should show 8 carbons in my diagram. One double bond here, single bond, double bond, single, double, single, double. So it is cyclic conjugated. Just like benzene, just like cyclobutane please. Now if I take this molecule, again, it is surprising. It undergoes reactions typical of a polyene. Polyene means nothing but alkene only, is it not? Suppose if I am adding bromine to this. Remember, when I add bromine to, I'll rub off this. When I add bromine to benzene, this is my benzene molecule. If I add bromine to this, it does not react unless and until you add a catalyst. And of course, it undergoes a reaction which is substitution, not addition. So at the end of some steps, I am getting what is called as bromobenzene. Whereas if I add bromine to this molecule, no catalyst, nothing, it immediately reacts and I get an addition compound, depending upon how many moles we are taking here. It definitely acts across the double bond. That means the reactions are contrast. It is substitution. This is addition here. Or if I take my bromine molecule, sorry, KMnO4 potassium permanganate, which is an oxidizing agent, and add to this benzene molecule, I showed that reaction also. If I add to my benzene molecule, MnO4 minus, this is a purple color, is it not? And there is no reaction. That means purple color will remain purple. Remember, potassium permanganate is an oxidizing agent. And once it is oxidizes, the purple color should change to either colorless or brown color. Now, if I add the same KMnO4 here, MnO4 minus here, the color vanishes because it is able to oxidize a double bond. That means the double bonds here and the double bonds here, I don't think they are comparable. I'm putting aside my cyclobutadiene, I'm comparing this to, even though both of them are cyclic conjugated systems, I don't think their behaviors are comparable. This is reacting in alkene, whereas cyclobutadiene was an anticlimax, it was very, very reactive system here. Therefore, cyclic conjugated systems enhance stability. I don't think we can just understand by extension of simple resonance theory. In fact, as a matter of fact, this particular molecule, later on structural studies indicated, it is not planar and it is going for a stable conformer, and that stable conformer is something like a tub shape. Tub shape. You can take a vessel, tub shape. In that tub shape, the planarity is of course sacrificed. Therefore, there is no question of delocalization. That is one more surprising thing. Merely having cyclic conjugated means it may not be like benzene. It may be like benzene, or it may be like cyclobutadiene, or it may be like this. Therefore, the correlation between conjugation and stability was slightly simple if it is non-cyclic. Suppose if it is cyclic, we are expecting a variety of behaviors. If I take benzene as the reference molecule for high stability, the other extreme of the spectrum is cyclobutadiene, which reacts immensely fast. It is difficult to isolate it also. If I take cyclooctatetraene, it is behaving like an alkene. Therefore, I require a better approach to understand the correlation between conjugation and stability by means not of no longer my valence bond theory, which is very good, but it cannot account why these molecules are behaving differently, even though all of them are apparently conjugated. So I require a new tool to understand their behavior, more so their stability. And this will try to work out in the next video. Thank you very much.